Hi. In this video I'm going to try to make sense of the connection between electric potential and electric field. And the key insight we're going to understand here is that the electric field is a vector that gives me the downhill slope of V. And mathematically we write it like this. E as a vector is minus the gradient of V. If this were in one dimension, we just says the E field, say the x direction, is minus the rate of change of V with respect to x. Like how steep does V increase as you increase x? Well, you put a minus sign in front, that's the electric field. Electric field kind of points down the hill. In 3D, or 2D say, there are different directions. So this is actually going to be a vector. And we're trying to understand what does this mean. Right? Whether or not you've done this in some calculus course doesn't matter. We're going to try to understand what it means conceptually. That's the key to really understanding a lot of what is to come. Whether or not you can do the vector calculus math that's involved here. Okay. So what you see here is a map of a part of Mount Rainier. I just picked a random part that looked good. This is, I guess, the Tahoma Glacier. And it's a what's called a topographical map. And if you've been hiking it all in the mountains, you probably have seen lots of them. Right? What you see on this type of map, if you follow those lines there everywhere across the map, those are lines of constant altitude. So this one here is at 8,400 feet, and if I imagine walking along this line, I always walk essentially along the side of the mountain without going up or down. Down here is 7,800, so I can sort of see, if we go from here to the left, go west from this point here, go this way, then I'm going down the hill. If I start here and I go this way, I'm going up the hill. Now, which way, if I'm situated here, is down? Well, anywhere to the left of this 8,400 line is down. But the steepest way down, if you imagine I put like a marble there, which way is it going to roll, is going to be essentially in something like this direction here. So you can see this, arrow here. Hard time doing this apparently. Right? This is the direction that points straight down the hill. It's perpendicular to those lines of constant height. If I am say over here, I'm at this, or let's go over here to the 7,800 line, like I'm somewhere around here, just above the T and the A, then down the hill would again be perpendicular to the line. That's a giant arrow. Let me make this a little bit smaller. There we go. Right, so down the hill would be in essentially this direction here. Again, if you're on a 7,800 line, here, down the hill could be any direction that's to the west of this line. But the straight line down the hill, the steepest direction you can walk, is going perpendicular to the line down the hill. And that's analogous to the electric field. If those are lines of constant electric potential, then the electric field points straight down the hill. The same way this arrow here points straight down the hill from there, and this arrow here points straight down the hill from there. The reason this analogy works is because these lines, they're lines of constant altitude, but you can also think of them as lines of constant potential energy. Right? If you walk along one of those lines, you're not going to change your gravitational potential energy. It stays constant. Now, but your gravitational potential energy is going to depend on your mass, right? mgh. Well, we could talk about a gravitational potential energy, say, per kilogram. Imagine you put a sort of a probe mass of 1 kilogram that you carry along the mountain. You ask, what is its potential energy? Then the potential energy would just be GH. You might call it the gravitational potential. right? Because it's per kilogram. That's the analogy of the electric potential, which is the potential energy per coulomb of a charge we sort of hypothetically place somewhere there. The analogy between those lines of constant gravitational potential, or the contour lines, constant altitude, and the analogy between those and so-called equipotential lines in electrostatics, meaning lines of constant electric potential, work extremely well, right? The downhill direction is the direction of the electric field, from higher potential to lower potential in the straightest line possible. You can also tell from one of those maps how steep the area is, right? So for example, if you look here, if I say here, downhill will be in this direction, sort of left and down. Let's move this arrow over here maybe. Right, it's going to look something like this. But actually, it's going to be fairly weak because this is fairly shallow. You can tell because the potential, meaning the height, doesn't change very much as you go from one point to the next. You have to move a large distance to have any significant change in the potential. Whereas let's move over here, let's move this arrow over here, right? Here the slope is much steeper, the lines are closer together, so you're going to change your gravitational potential more quickly as you move sideways. So in this case, I might draw the potential something like this, right? Perpendicular to the line of constant potential, and longer than this one because it's steeper down, right? The slope has a greater magnitude because it's way faster to change potential as you walk here west than walking here west. Let's now go to an actual application in electrostatics. So what I've got here is the simulation that you already know, you've met before. Now I set it up in such a way that I've got a couple of charges here, a couple of charges here, and some negative ones here, right? Just because. And now in the simulation, if you go on it, you get one of those potential meters. It measures the potential. So let's just draw some equipotential lines. So let me find a line that says 50 volts, as close as I can get it. 49.86, that's good enough. I'm now going to press this button, and it's going to show me the line of constant 50 volts. Let me go to 40 now. So 41, 40, that's close as we're going to be, 40.09. So now I'm going to plot the line of constant electric potential being 40 volts. Looks like this. Let's go down to 30. Do a bit better than this. Oops. There we go, 29.9. Looks like this. Go down to 20. Go down to 10. I'm making sure that I'm plotting those lines equal voltages apart, right? It's crucial. I'm not plotting them at 20, 15, 12, 11, but I'm plotting them in this case 10 volts apart. So I go to 0. Note that 0 doesn't mean the bottom, right? You can go to negative values, as long as there's some negative charges somewhere. That's as close as we're going to be. And let me do minus 10 now. You can tell it happens closer to the negative charges. Maybe let's try minus 20. Something like this. Close enough, right? Good enough for our approximation. So what I've drawn now is a contour map for my potentials. And these ones were the highest, these ones were lower down. So it's almost like there's this hill up here, this mountain with two peaks. And then there's this valley down here where the potential becomes negative. Now if I then use my sensor, right, the sensor shows me, in the simulation, direction of the force on my probe charge. And you can tell that the probe charge, the force is less here than it is, say, here. Right here, it goes off the screen. The force is so big, the arrow goes off the screen. The lines are fairly close together, whereas here, the arrow that shows me the force is a lot shorter. I can move it around over here. Again, it becomes very short. The lines are far apart, but it always points down the hill. If you go along a line, it's always perpendicular, but the length of it depends on how steep the lines are together. So here they're, not super steep, but fairly steep compared to, say, here, where they're really far apart. So here the electric field, represented by this arrow, the force on one probe charge they're moving along, is lower. So this arrow also shows me this grad of the potential, right? This strange calculus, vector calculus concept that can be hard to interpret when you first meet it. The electric field is down the hill. Let me just add a couple more voltage readings. Let's say I go up here. So this one here was 50. Let's go to 60. Add a couple more. And then go to 70. Perfect. Okay, and then maybe we can find a 70 over here as well. There you go. Okay, so now you can actually see that this is indeed two peaks, right? So they're not. There's an area in between here that's a bit lower. You can imagine if this were mountains, you walk from one peak down the hill, and then there's the lowest point here back up the hill. Or you can turn and keep going down, 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 further down into this crater here, where the minus charges are at the bottom. One thing to note is that suppose I place a charged particle here, positive charge, and I let it go, right? It's going to initially accelerate in the direction of the force. It's too big here to fit on the screen. Then it might roll to, say, here, and now the force is down the hill this way. It doesn't mean it's going to always roll in that direction. You can imagine I give it a sideways push, or it might have gained some sideways velocity from starting out here. So it's moving this way, and it actually sort of turn around like this, right? So important thing to note is the electric field lines, direction of the electric field at every point, they are not the trajectories of a charged particle, because they indicate the direction of the acceleration, and the magnitude of the acceleration that's proportional to the force, not the direction of the velocity. That's a crucial thing to be aware of. Let me remove the probe charge. Let me just put the electric field on, those arrows. You can sort of see nicely how they point out down the hill, wherever you go. Like down the hill here, always perpendicular to the lines of constant potential. So this analogy between the gravitational potential that you can see directly on a contour map and these contour maps of electrostatics, this analogy works extremely well. It's going to help you through the whole topic of circuits as well. One thing to be aware of, though, is of course really these should be not lines, but three-dimensional surfaces. Of course we can't see that on a screen, right? But because we live in three-dimensional space, really it's not a sort of circular shape around it. It's a closed sphere around it. We have an equipotential surface rather than just an equipotential line. Right? That analogy doesn't work with the side of the mountain, because the side of the mountain is essentially a two-dimensional surface. It's sort of bent in the three dimension, but you can't choose to sort of, like, you can only choose to go left, right, forwards, backwards. You can't choose to literally go vertically up or down, right? That's why we can draw it on a map in the first place. Whereas electrostatic potentials, they're really equipotential surfaces, not lines. But this visualization as lines in a 2D space, I think, helps a lot to make sense of it, and to understand the analogy with the gravitational field on the side of a mountain. All right, I hope just that intuitive idea helped to make sense of it. The math, okay, that's a different story, and we're going to cover that elsewhere.